Welcome to the deep dive. So today we have a really specific mission tailored for you, the learner. We are opening up this massive stack of highly technical engineering docs, CTO pitches, and some market briefs.
Yeah, it's a lot of data.
It really is. And we're looking specifically at this seismic shift happening right now in the AI hardware landscape. And we're in 2026 now, and usually when we think about AI, the image that comes to mind is like a giant humming data center spending months just training a single monolithic model.
Right, like building an encyclopedia from scratch.
Exactly. But here's a mind-blowing fact to just kind of kick things off. That era of training being the main event, it's over. As of early 2026, the inference flip has officially happened.
Yeah, and it really is a fundamental pivot for the whole industry. Like, training is still important, obviously, but running the models, actually using them to generate answers or process documents, that phase is inference.
Right.
And inference now consumes about 2/3 of all global AI compute. Yeah, it's a massive jump. I mean, it was just 1/3 back in 2023. We're looking at an inference chip market exceeding $50 billion today.
50 billion. Okay, so let's unpack this, because to understand why this flip is so critical and really why we are looking at a specific custom silicon challenger today called CortexPod, we have to look at how the workload itself has, well, fundamentally shifted. Because we aren't just running single chatbots anymore, right?
Not at all. I mean, enterprises today, they've moved way beyond that simple prompt and response dynamic. They're running what we call agent meshes.
Agent meshes.
Right. So let's visualize a very real scenario. Imagine a complex loan application pipeline at a major bank. A 200-page application comes in, and it's full of PDFs, tax returns, all of that. You don't just ask one single AI model to make a definitive decision on all that.
Right, because that would be incredibly prone to hallucination.
Exactly. It would just hallucinate. Instead, you deploy a mesh of specialized agents. You have, say, a researcher agent that exclusively extracts the financial statements. And then it hands that specific data off to a risk scorer agent, which is concurrently checking regulatory databases. Then that agent passes its results to a compliance auditor, which finally feeds everything to a summary writer.
So they're all working at the same time.
Exactly, concurrently. They are all sharing that same 200-page loan application as their source context. And most importantly, they're passing intermediate states back and forth to each other in real time, literally hundreds of times per second.
Okay, so this right here is the core problem that CortexPod is trying to solve. Because GPUs like the famous NVIDIA H100, they were built for the old world of like single model oracle processing.
Right.
You ask a math question, you wait, you get a massive answer.
Yeah.
They were absolutely not built for these highly distributed communicative agent meshes.
Precisely. I mean, GPUs are marvels of engineering, but their architecture was locked in when that single model sequential decode was the main thing. Think of a GPU like a massive freight train.
Okay, a freight train.
Yeah, if you need to haul 10,000 tons of coal in a straight line, the freight train is unmatched. But an agent mesh isn't a straight line. It's more like 100 different pizza delivery scooters weaving through a dense city grid, constantly handing off packages to each other.
Right.
If you try to run that financial pipeline on a standard GPU, you are basically forcing the freight train to do the job of the scooters. It technically works, but it's just wildly inefficient.
And the data actually shows the market reacting aggressively to that inefficiency. Like, if GPUs are the wrong tool for the job, what is the right one? According to the market briefs in our sources, custom ASICs, application-specific integrated circuits, they are absolutely crushing GPUs in growth right now.
They really are.
Cloud service provider custom ASIC shipments are growing at 44.6% annually. Compare that to GPUs, which are at just 16.1%. And the ASIC share in AI inference has jumped from 15% in 2024 to a projected 40% this year in 2026.
And what's really fascinating here is that even the incumbent, even NVIDIA, is publicly validating this architectural mismatch.
Oh, really?
Yeah. Look at their massive GTC 2026 announcement. They announced this disaggregated inference thing. They released Dynamo OS to actually split their own inference pipeline in half.
Split in half how?
So they're running the compute-heavy prefill phase, where the AI reads the initial prompt on their Vera Rubin GPUs, but then they are offloading the memory-heavy decode phase, where it actually generates text to completely different hardware, the Grok LPU racks.
Wait, so if I'm understanding this, it's almost like Like a high-end restaurant realizing their master executive chef, the GPU, is way too expensive and slow to spend time just chopping vegetables.
Yes, perfect analogy.
So they're literally splitting the kitchen line across two completely different buildings
Right.
and hiring a whole new coordination team just to ferry the half-prepped food back and forth.
Doesn't NVIDIA splitting their own pipeline kind of prove they're trying to use a software band-aid to solve a physical hardware bottleneck? It absolutely does. They are architecturally dismembering the GPU pipeline to try and solve exactly what CortexChip is designed to solve natively right there in a single piece of silicon.
Wow.
It's a profound market signal. In fact, our sources highlight a March 2026 quote from IBM that really anchors this shift. They stated, quote, "A new class of chips for agentic workloads will emerge," unquote. And CortexPod represents this exact new class.
So if NVIDIA is using like software orchestration to stitch things together across different chips, how does CortexPod solve this physically in the silicon? The engineering docs we have, they outline 5 highly defensible architectural advantages, or moats.
Right. 5 distinct moats.
Let's look at the first major bottleneck,
Yeah.
the handoff. How does CortexPod physically build a chip for those pizza delivery scooters instead of the freight train?
So they do it with a component called the CortexMesh Fabric Controller, or the CMFC. This is a dedicated silicon block that you simply will not find on any general-purpose GPU. You can think of it as the dedicated synaptic circuit for these AI agents. It acts as a hardwired router for the mesh, and it allows for sub-2 millisecond inter-agent handoffs.
Sub 2 milliseconds. To put that in perspective for you listening, if you run that exact same agent handoff on a fully loaded H100 GPU using their CUDA software scheduling, it takes 50 to 200 milliseconds.
Which is an eternity in compute.
Routing through the central memory using software is the CMFC essentially building like secret physical tunnels directly between the specific processing cores.
That is a brilliant way to visualize it. Yeah. The hardware bypasses the host memory entirely. It transfers a state directly on Fabric. And if we connect this to the bigger picture, think back to that financial pipeline.
Loan application.
Exactly. If you have 32 agents making just 10 exchanges per document, that GPU software delay adds up to 2 full seconds of pure coordination overhead per document.
That's 2 seconds of dead air before a single word is even generated.
Right. And the critical point is that you physically cannot emulate this CMFC hardware in software without incurring a massive 10 to 25x latency penalty. It has to be baked into the physical chip design.
Okay, so the CMFC silicon tunnels, they solve the delay of passing the baton between agents. But what happens when you scale up? Like, what if you have hundreds of runners on the track at once? Because a GPU would just trip over itself, swapping out all those different memory.
It totally would. And that brings us to their second major moat, the sheer scale of concurrent contexts. CortexChip has 256 concurrent agent contexts.
256.
Yeah, that means 256 hardware priority lanes. Contrast that to the mighty H100, which maxes out at about 8 concurrent contexts before it starts, painfully swapping memory in and out.
Why does a GPU start thrashing at just 8?
Because the GPU memory subsystem was designed to push one massive weight matrix through the pipeline as fast as possible. When you try to juggle more than 8 active agents, the GPU has to constantly flush and reload massive chunks of data from its memory. It's just a huge traffic jam. The fact that CortexPod can natively run a 32-agent pipeline simultaneously on a single chip without that context swapping, that's an architectural reality at the silicon level. It's a physical gap in the hardware design, not just some software limitation that can be patched over later.
So we've got the runners, we've got the lanes. What about the baton they're passing?
Yeah.
The data itself. Because, computing power is great, but moving data around is usually where the real bottlenecks hide. And here's where it gets really interesting.
Oh, definitely.
Because CortexPod tackles that memory traffic jam directly with a hardware-shared KV cache.
Yes. So the KV cache, the key value cache, is essentially the AI's short-term memory of the document it's currently reading. And the redundancy problem on GPUs here is severe. Remember, those 4 different agents reading that same loan application.
Yeah.
On a standard GPU cluster, the hardware actually computes the full KV cache 4 separate times. It duplicates that massive data footprint 4 times because it has no native hardware mechanism to just share it across different agent processes.
It's literally like printing 4 physical copies of a massive 1,000-page textbook, putting them on 4 different desks in different rooms, and having 4 workers read the exact same chapter completely independently.
It is incredibly wasteful. GPUs have to rely on clunky software synchronization techniques like prefix caching to even attempt to reduce this. And even then, the first agent always pays the full compute cost.
Right.
But CortexChip does this at the hardware level. One computation, 4 reads. It uses a hardware shared read bus, so it's literally wiring the physical memory cells so that multiple processing cores can tap into the exact same electrical signals simultaneously.
So using our analogy, CortexPod essentially puts one physical textbook in the center of a glass table, and all 4 workers just read it at the exact same time from different angles.
Exactly. So instead of an 84-gigabyte memory footprint for those 4 agents, it's just 21 gigabytes. 75% of that redundant compute is eliminated natively, automatically, with 0 complex software orchestration required.
That's huge. And they aren't stopping at just a single chip either. Our sources bring in some cutting-edge 2026 research on CXL Compute Express Link, right? Proving how critical this memory management is at scale.
Yeah, the TrackCT system research.
Right. It shows that offloading the KV cache to CXL attached memory reduces GPU memory usage by an incredible 87%, while still maintaining a sub-100 nanosecond access latency.
CXL 2.0 is just revolutionary here. You can think of it as a universal ultra-high-speed umbilical cord between servers. Previously, if a chip ran out of its own onboard memory, it had to fetch data over a slow network connection.
Which just cripples the AI speed.
Completely cripples it. But CortexPod leverages CXL 2.0 to scale out across entire clusters. It effectively turns rack-scale memory pooling into a native hardware feature.
Wow.
It allows these chips to talk to each other and share that KV cache across a whole server rack almost as fast as if the memory were sitting on the exact same physical chip. It makes an entire server rack feel like one giant unified brain to the software.
All right, so conceptually, we've established it's a brilliant chip. It solves the handoffs, the concurrency, the memory duplication. But we have to step out of the server rack and into the physical reality of 2026. Can they actually build it and sell it in this, fractured global supply chain?
This is a vital point, and it's their 4th major architectural advantage. A TSMC-free supply chain.
TSMC-free.
Right. To understand why this is a massive moat, we have to look at the enterprise realities of the market today. The Asian marketplaces like Vietnam, India, Singapore, they are leading deployment environments for these agent meshes, but they require local data processing.
Okay.
And from a purely procurement perspective, enterprise CTOs in those regions view total reliance on TSMC in Taiwan as a massive supply chain liability, mostly due to tightening U.S. export controls.
Right. And just to be clear, we are looking at this impartially as a regulatory reality. Like if export rules tighten further, a bank in Mumbai could see their entire AI infrastructure paralyzed overnight simply because they can't import the chips anymore.
Precisely. It's an enterprise risk management argument. CortexPod's brilliance here is their process node decision. They aren't trying to use the absolute most cutting-edge 3-nanometer or 5-nanometer TSMC nodes.
Which everyone else is fighting over.
Right. Instead, they're using a highly mature 12-nanometer FinFET process, specifically Samsung SF12 or GlobalFoundries 12LP Plus Night. FinFET is a highly reliable, older 3D transistor design, and they pair it with standard ASE FOPLP packaging.
Okay, you're going to have to give me the explain it like I'm 5 version of ASE FOPLP packaging.
Oh, of course. So usually advanced chips use something called CoWoS chip on wafer on substrate.
Sounds expensive.
It is, and it relies on TSMC's highly constrained silicon wafers to package the chips together. It's a massive bottleneck for NVIDIA right now. FOPLP stands for fan-out panel-level packaging. Instead of relying on those expensive circular silicon wafers, FOPLP builds and connects the chips on large rectangular panels.
Oh, interesting.
Yeah, it's almost like printing circuit boards on giant sheets of glass. It's significantly cheaper, much more widely available, and entirely bypasses the TSMC bottleneck.
Meaning zero CoWoS dependency.
Zero.
By avoiding TSMC and CoWoS entirely, CortexPod can actually manufacture and ship these chips to the Asian market today, legally and reliably. It provides supply chain independence, which I guess is a mandatory feature for these buyers, not just a nice to have.
Exactly.
But I do have to push back here. 12 nanometer is ancient compared to the 3 nanometer chips everyone else is racing to build. If I'm playing devil's advocate, We are compressing everything to fit on this older 12-nanometer chip and relying on lower memory bandwidth with standard GDDR7 memory instead of ultra-fast, high-bandwidth memory. Aren't we just dumbing the AI down to make it cheaper?
It's a very fair critique, and it actually brings us perfectly to their final advantage.
Okay.
W4A8 hardware calibration assist.
Okay.
You are right that inference is fundamentally bound by memory bandwidth. To make that older 12-nanometer silicon and standard GDDR7 memory work, CortexChip has to use W4A8 quantization.
Which means?
That means compressing the model weights down to 4-bit integers and the activations, the intermediate math the AI does, while thinking down to 8-bit integers.
Which shrinks the physical size of the model by about 4 times, letting it fit on the older hardware. But normally, squishing the math down that much causes the AI to lose a lot of its reasoning accuracy, right? It's like compressing a high-res photograph into a tiny JPEG. Usually you lose a ton of detail and the image just gets blurry and pixelated.
Normally, yes. Software-only W4A8 quantization causes a noticeable drop in accuracy because the compression is static. It's blind to the actual data flowing through it. But CortexChip doesn't just rely on software.
What do they do?
It includes dedicated hardware calibration assist registers physically built into the chip. This physical hardware tracks activation statistics in real time, things like the mean and variance of the data, and feeds a correction unit that applies dynamic scale adjustments during the inference process itself.
So using our photo analogy, CortexPod essentially has a built-in upscaler right in the silicon that anticipates exactly where the blur will happen and sharpens those specific pixels in real time before the final image is even rendered.
That is exactly how it works. It fixes the compression errors on the fly. And by doing this in hardware, it recovers 0.3 to 0.5 percentage points of the accuracy that is typically lost to software-only quantization.
Wow. So where does that leave the final accuracy compared to, a massive uncompressed model running on a massive GPU?
It lands at just a negative 1.4% accuracy loss compared to running heavy, full-precision FP16 models on standard benchmarks like MMLU.
Only 1.4%.
Yeah. And for enterprise use cases, legal contract analysis, financial auditing, regulatory document processing, a 1.4% drop is virtually imperceptible. It's well within acceptable thresholds. It is the perfect good enough for production AI, delivered at a fraction of the power footprint and hardware cost.
So what does this all mean for you listening right now? Let's try to pull this all together. We've gone from a world of single AI oracles sitting on expensive bottleneck GPUs to a world of distributed multi-agent meshes running on custom silicon.
A completely different landscape.
Yeah, and we've seen how CortexPod uses these 5 distinct modes: the CMFC router tunnels, the 256 hardware priority lanes, the shared KV cache with CXL memory pooling, the TSMC-free glass panel supply chain, and finally, the real-time hardware quantization upscaler to completely rewrite the economics of running AI.
It really is a paradigm shift. It's moving the entire industry away from optimizing for a single massive computation and instead optimizing for communication and coordination between many smaller computations.
It's funny, looking through the sources, they mentioned CortexPod's logo.
Yeah.
It's a 6-lobed brain with each lobe a different color: blue, green, orange, purple, dark gray, red.
Yeah, I saw that.
And after unpacking the mechanics of all this, you realize how perfectly it represents their hardware. Each lobe is a different agent: the router, the researcher, the writer, the compliance agent. They are all operating in parallel, sharing context seamlessly on one physical silicon substrate, producing an outcome none of them could produce alone. It really is the brain as a distributed system.
That's a great observation. And I think I'll leave you with a final thought to mull over regarding all this. For the last decade, our imaginations for what AI software could do have been secretly constrained by the physical limits of GPU memory architecture.
Right.
We thought in terms of single prompts and linear responses because the hardware dictated that bottleneck. But if chips like CortexPod make agent meshes practically free and instant, removing those latency penalties entirely, we might see the rise of something entirely new: ephemeral agents.
Ephemeral agents.
Yes. Imagine AI agents that are spawned into existence for a single millisecond just to fact-check one specific word in a massive legal contract, cross-reference it with a global database, report back, and then immediately die. The future of AI might not be massive, godlike oracles sitting in a data center. It might be trillions of microscopic, disposable digital workers swarming over a problem in fractions of a second. When the hardware limits disappear, the software gets to dream a completely different reality.
Trillions of disposable digital workers. That is exactly the kind of question we love to leave you with. When the hardware limits disappear, the software gets to dream a little bigger. Thank you so much for joining us on this deep dive into the agent mesh era. Stay curious and we'll see you next time.